So let's start looking at errors in measurement and how that affects how a scientist, how reliable a scientist's data are. So all measurements have some kind of error or uncertainty associated with them. For instance, my tape measure may say I'm 179 centimeters tall, but a more precise tool might say that I'm 179.07 centimeters tall. No measurement is known to an infinite number of decimal places. Scientific measurements, therefore, must show this limitation. Any measuring tool will have some limitation. And scientific measurements show that limitation by expressing measurements with the correct number of significant figures, which we call sig figs for short. Significant figures indicate the precision of a measurement, how precise the measuring tool is. So again, is a person 2 meters tall or are they 1.91 meters tall? Okay, that level of precision, how many decimal places can you say are accurate in that measurement? When you record the sig figs in a measurement, you need to include every digit you know for certain, plus one more digit that is uncertain, an extra digit that you estimate, you make your best guess on. So, to give an example of how this looks, on this ruler, the clip length is definitely between 2.3 and 2.4 centimeters. I'll add in the dotted line there. We need to estimate one more digit. So if I think that paper clip is about halfway between the 2.3 and the 2.4 mark, we say that it's 2.35 centimeters long. Now that last digit is uncertain. I think it's 2.35, but you might think it's 2.34 and someone else might think it's 2.36. That's okay. That last digit is uncertain. And on a test, I would accept a range of answers, but I would expect every answer in this example to be somewhere between, 2.32 and 2.38. I would expect you to have an answer in that range, okay? So let's look at other kinds of measuring tools, like a triple beam balance. When you're using a triple beam balance, you have to add the values on each beam. So in this example here, I have a 300 grams on the hundreds beam, 20 grams on the tens beam, and here on the grams beam, I have 9.4. It's definitely more than 9.4, but it's not all the way up to 9.5. So let's call that 9.46. And when I add those values together, I get 329.46 grams. Now that last 6 is uncertain. So again, you might think it's 329.47. That's okay. We give every digit that we know for certain plus one more digit that we do not know for certain. When you're reading a graduated cylinder, remember that you need to read the volume at the bottom of the meniscus and you need to read the meniscus at eye level. You should always check the meaning of each mark because one mark does not necessarily equal 1 mil. So here we have 3 mils and 4 mils, but only 5 spaces between those. So each space represents 0.2 mils. So we've got 3.2, 3.4, 3.6, 3.8, 4.0. So if we're halfway between the 3.4 and the 3.6 mark, then we would say that, then we would say that this is about 3.5, okay? Halfway between the 3.4 and the 3.6. So we need to be able to label how many significant figures are in a particular number. And there are some rules that will help us do that. So 5 rules. Different textbooks break these rules down in different ways, but I like to think of this as being 5 rules. So rule number 1, non-zeros are always significant. So here for the number 96, both of those digits are non-zeros, so there are 2 significant figures in that number. For 61.4, again, all of those digits are not zeros, so there are 3 significant figures in that number. Rule number 2, captive zeros are always significant. And what do I mean by a captive zero? I mean a zero that's stuck between some non-zero numbers. So the 0 in 5.029 is captive. It's stuck between a 5 and a 2. So that all of the digits in 5.029 are significant. That number has 4 significant figures. Similarly with 306, that 0 is between the 3 and the 6, so all 3 of those digits are significant. The next rule, rule number 3, leading zeros are never significant. They're not significant because they are just used as placeholders. And what I mean by that is if you're writing 0.4 and comparing it to 0.004, those are 2 different numbers, right? 0.4 is much bigger than 0.004. We need those zeros there as placeholders. We can't throw them away. They're important, but they're not significant. They don't help the measurement be more precise, okay? So in this example, 0.095987, I've underlined the only significant figures, the only significant digits in this number. These leading zeros are not significant. Similarly, 0.004084, that has 4 significant figures because these leading zeros are not significant. Trailing zeros, this is rule number 4, trailing zeros are not significant when there is no decimal point. Again, these are zeros that are used as placeholders. If you've got either $50 or $5,000, there's a difference there. Those zeros are important as placeholders, but they are not significant. So here, 9,300, that number has just the 2 underlined significant figures. The trailing zeros are not significant. Similarly, with the number 200, there's only 1 significant figure there. Those zeros are not significant. Lastly, trailing zeros are significant when there is a decimal point. It means that the measurement is very precise. When we include that decimal point, it means that all the digits after it are meaningful. So with 9,300, this tells us, that decimal point tells us that all 4 of those digits are significant, that we measured 9,300 very carefully, and we know the 9 and the 3 and the 0 with certainty, and 0 is our best guess at that last digit. So all 4 of those digits are significant. Similarly, with 410.00, that number has a decimal point, so all of those zeros are, trailing zeros are significant, 5 significant figures. For 802.3010, all of those digits are significant. We've got a captive 0, and a trailing 0, and a number that has a decimal point. So all of those are significant, 7 significant figures. Summary rules. So here are the kind of summary of those 5 rules, if thinking about it this way helps you. All numbers are significant unless they are only used as a placeholder. So leading zeros are always just placeholders, so you never count them. And trailing zeros can be just a placeholder. It depends on whether the number has a decimal point or not. Trailing zeros with no decimal point are just placeholders, so you don't count those. But if a trailing 0 is in a number with a decimal point, then you do count that as significant. Okay, so let's practice this. How many sig figs are in each of these numbers? And just for practice and to make sure that you're looking at those rules and trying to apply them, I want you to write in parentheses how which rule you use to figure out how many sig figs were in the number. So pause the video, give it a shot, and come back and check your answers. Okay, so for the number 86, this number has 2 significant figures, and I used rule number 1 because non-zero numbers are always significant. Similarly, for number 2, we have 3 significant figures, and again, I used rule number 1. All non-zeros are significant. For rule number 3, it's only when we start to see zeros that we have to start being careful. Here, those zeros are significant. This number has 5 significant figures because I used rule number 5. Trailing zeros are significant when the number has a decimal point. Number 4, this number has only 1 sig fig because of rule number 4, which says trailing zeros are not significant when there is no decimal point. Number 5, 0.00725 has 3 sig figs, and I used rule number 3 for that because none of these leading zeros are significant. For question 6, 82.0 has 3 significant figures because we used rule number 5. That trailing zero is significant because the number has a decimal place. 0.0051 has just 2 sig figs because of rule number 3. Those leading zeros are not significant. And lastly, 95,010 has 4 significant figures. The first zero is significant because it's captive. That's rule number 2. But the second zero is not significant because it's a trailing zero and the number does not have a decimal point. So that's rule number 4. Okay. So let's look at how we apply these rules when we're doing addition and subtraction. When you are adding or subtracting, the place value of the last significant figure of the least precise number in the problem, so I'm talking about the hundredths place, the tenths place, that determines the place value of the last sig fig in the answer. So basically, you can think of it as being the number with the fewest decimal places determines the number of decimal places in the answer. We're not necessarily talking about decimal places if the number doesn't have any decimal places, but that's a shorter way to talk about it than saying the place value of the last significant figure. Okay, so let's look at how this looks in practice because the rule is almost harder to say in words than it is to see how it functions. So here we have 3.756 plus 4.1, and if we plug that into a calculator, we get the answer 7.856. But when we're in chemistry, we can't trust our calculator anymore. The calculator doesn't always give us the final right answer. So what we're going to see here is that because 4.1 is the least precise number in the problem, it only goes to the 10th place here. That's going to limit how many decimal places can be in my final answer. So because after the 10th place, that's where my least precise number got cut off, I'm also going to need to round off my answer at that 10th place. So because the number after the line is 5 or above, that rounds up that 8, and that 8 gets bumped up to a 9. So the final rounding here is 7.9 mils for my answer. Let's look at another example. If I have 224 plus 130, that gives me 354 grams. Again, what's my least precise number here? 130, only my tens place here is significant. This is a trailing zero and a number without a decimal point, so that is not significant. Therefore, I'm going to have to round off my answer after the tens place. And because this number is less than 5, this has no effect on the previous digit. And we just round off to 350 grams. Please note, sometimes when students draw this line here, they just want to cut the number and just write the number 35. 35 is not the same as 350. That 0 is important. It's needed as a placeholder. Another mistake that students often make is they just truncate the number, they forget to round. And so they would write 7.8 as the answer here. I need you to round your answer, not truncate. So don't do this. Look at the number after the dividing line and decide whether you need to round up or keep the value as shown. All right, so it's time for you to do some practice problems. So give it a shot, pause the video, and come back and check your answers. For question 1, if you just plugged this number into your calculator, you would get the answer 150.97. But that's not the answer we're going to write here. Here we go to the tens place. Here we go to the hundreds place. We're going to have to trim our answer after the tenths place. Because this number is 5 or higher, we're going to need to round up. But when we round up, this becomes a 10. So what we're actually going to do is we're going to have an answer of 151. Now, remember, I want to include the tenths place here. That tenths place is significant. Therefore, don't just write 151. That would be an incorrect answer. I want to keep that tenths place here, but the 9 did get rounded up to a 10, so it's now a 0. So this is our final answer. Looking at question 2, if you plug this number into the calculator, you would get 123.279. However, my first number only has 1 decimal place, my second number has 3 decimal places. So in reality, I can only go to 1 decimal place in my answer. Again, this number is 5 or higher, so I'm going to round up, and my final answer is 123.3. Oops, didn't circle that right. There we go. Question 3, if you plug it into your calculator, you get 3.41, but since, let's see, this number has 2 decimal places, but this number only has 1, therefore my final answer can only have 1 decimal place. And this time I don't round up, I just have a final answer of 3.4. And for question 4, again, if you plug this into the calculator, you get 7.45. But let's see, 2 decimal places, 1 decimal place. My final answer can only have 1 decimal place. I'm going to need to round up because this number is 5 or above, and you get 7.5. Okay. I would say that this type of problem students often find trickiest just because of that extra 0. Students just forget to include that. So that's how you do addition and subtraction with appropriate significant figures. Let's look at how we do multiplication and division. The rules are different. So it might help you to do some more practice problems with addition and subtraction to get that solidified in your head before you look at the multiplication and division examples. When you are multiplying and dividing with significant figures, the number with the fewest significant figures in the problem determines the number of significant figures in the answer. So, for an example, 13.91 times 23.3 gives you an answer on the calculator of 324.103. The first number in the problem has 4 significant figures. All of those digits are significant. The second number in the problem has 3 significant figures. Again, all those digits are significant. Because I have 4 significant figures and 3 significant figures, my answer is going to be limited by this number. My answer can only have 3 significant figures in it. So I need 3 significant figures in my answer. 1, 2, 3. This is where I trim, this is where I do my rounding. This number is less than 5, so I just have 324 as my final answer. There are 2 situations where a quantity has an infinite number of sig figs, and therefore, even though the number may look like it doesn't have a lot of sig figs, it does not have an impact of the number of significant figures in your final answer. These 2 situations are counted quantities. So for instance, if I'm averaging something and I divide by the number of people that I've counted. I counted 3 people, even though the number 3 only has 1 significant figure, because it's something that I counted, it's considered to have infinite significant figures. Similarly, a definition like 1 inch equals 2.54 centimeters. That's a definition. Even though it looks like this number has 3 significant figures, we treat it as having infinite significant figures, and this is not the limiting factor in a calculation. So let me show you what that looks like. Here I'm calculating an average. I don't know what this is. Maybe this is number of candy bars eaten in a day. One person ate 7.3 candy bars, one person ate 9.4, and one person ate 8.30 candy bars. And then we're dividing by 3. So first of all, let's think about our order of operations. We have to add everything in those parentheses first. And when I add those together, I need to follow the rules for addition. That was the last slide, remember. So when I follow those rules for addition, I find that I can only go to 1 decimal place because I have 1 decimal place, 1 decimal place, 2 decimal places. I can only go to 1 decimal place. That's my limiting factor. So I add them up and I go to 1 decimal place. So now I'm left with 25.0 divided by 3. 3, because this is an average, this is a counted quantity. So even though it looks like I have 3 sig figs divided by just 1 sig fig, really this is infinite sig figs. That's the symbol for infinity. Infinite sig figs. So my final answer can be reported to 3 significant figures. So your calculator will give you 8.33333, however many repeating 3s will fit on your calculator screen. But we're going to report this to 1, 2, 3 significant figures. Oh, looks like I did centimeters, not number of candy bars. That's fine. It would be a little weird to eat 9.4 candy bars. Okay, so it's your turn. Do these practice problems and pause the video and then restart so we can check our answers. So for question 1, your calculator will give you the answer of 35.7182. But this number has 4 sig figs, and this number has 3 sig figs. Therefore, our answer can only have 3 sig figs. So we trim the number here, or round the number here, and we get 35.7 as our answer. 6.62 has 3 sig figs. 2.5 just has 2 sig figs. So although the calculator tells you that the answer is 16.55, we can only have 2 sig figs in our final answer. So we do the rounding and we get 17 as our answer. 4.6354 has 5 sig figs. 5.621 has 4 sig figs. So my final answer just has 4 sig figs. So even though the calculator tells me that the answer is 26.0555834, we're going to need to round that off after 4 significant figures. Do the rounding and you get 26.06. And lastly, 13 divided by 6.50. If you put the problem into your calculator, you find out that the answer is 2. However, 13 has 2 significant figures and 6.50 has 3 significant figures. So our answer should have 2 significant figures. Right now I only have 1 significant figure. Where do I get another significant figure? By adding in a decimal point and a 0 after the decimal point, this number now has 2 sig figs, and this is the correct answer for chemistry. It shows the level of precision reflected in the measurements. Now, so far, I haven't really been dealing with units yet. It is important in chemistry to always include units with your numbers, but here I've been focusing on the numbers themselves. But as we progress through the module, we're going to need to focus more on those units.